We have introduced the relation between stress and strain in a general setting as epsilon equals a relation between stress and strain. And remember, if you want to recall what this matrix that goes in there is called, for a given amount of stress, you get a certain amount of deformation. The more deformation, the more compliant it is, and then you recall the joke. It's not a C, it's an S. So that's our compliance matrix. And now I'd like to go ahead and write that matrix in the special case when we have actually isotropy. So this is always true, it turns out, but we're going to first go ahead and remember what we have in the case of generalized Hooke's law for isotropy. So I'm going to write the shear components in the same order as I preferred using in epsilon. So epsilon gamma yz goes first, and then I cycle. Next goes gamma zx, and then gamma xy. And it's easy to remember what these are. Tau yz, by this time we've used it a lot. Tau zx, 1 over g tau xy. And here we have 1 over the Young's modulus, the stress in the corresponding direction, and then yc. For an isotropic material, I will construct the form of S, but what I do suggest is that you don't try to memorize the form of S. There is no need, because we already know the stress-strain relation in the form of generalized Hooke's law by heart. So I think that is more than sufficient. Okay, so I'm spending time writing these out explicitly because I think it is instructive. So now we have the general form and I have the specific form for the case of isotropy. And now I'd like to write this in that form just to understand what is going on. And again, I won't be lazy and I will write down explicitly all the components. Okay, first on the right we have stress, sigma x, sigma y, sigma z. And what I'm going to do is I'm going to split these up also through the middle as I've done before. I'm actually going to split this up as well in this fashion. I just remember that this is a 6 by 1, this is a 6 by 6, and this is a 6 by 1 array. And so now I have tau yz, tau zx, and tau xy. And here we have gamma xy, gamma zx, same ordering, gamma yz, and here epsilon x, epsilon y, epsilon z. All right. So I want to go ahead and write this set of equations in linear algebra form. So that is rather straightforward. So let's first go ahead and write the diagonal components. The diagonal components are, well, so for instance, epsilon x multiplies sigma x 1 over e, right? Epsilon x is equal to 1 over e. Sigma x, same for y, same for z. Of course, there are other terms, I'm going to write them. So gamma yz is 1 over g tau yz, 1 over g, and 1 over g, right? So then, first of all, let's concentrate on the shear stresses. Now, for shear stresses, there is no relation between a shear strain and a shear stress. So in other words, well, how would I calculate a value of gamma y, the value gamma yz. In order to calculate this, I would take the corresponding row of the matrix, multiply it with this array, and the result, this component summed with that, the second multiplied with that, and sum, and so on, would give me that quantity, right? So, well, I don't see any normal stresses appearing in there, and therefore I must have zeros here. Same for every component of the shear strain. So I have a big zero matrix in there. And here as well, I have a big zero matrix because no component of the normal strain depends on the shear stresses. To calculate epsilon, I would take that row, multiply it with this vector, and I don't see any tau appearing in that outcome for any normal strain. So that's a big zero as well. Now, moreover, any component of gamma corresponds to only its own, is related to only its own shear stress tau. And therefore, gamma yz is only related to tau yz, which means here we have 0 as well. Okay? So here we have all zeros. Now, but that's not the case for the off-diagonal components here, because epsilon x is related to sigma yz. I take this, multiply by that, I'm supposed to get epsilon x. So here I have minus nu over e, minus nu over e, and likewise for the other ones as well. All right. So this is the way the stress-strain relationship looks in this generic form for a isotropic material. What I've done is I have written explicitly what this compliance matrix is. That compliance matrix is this matrix. That's the form of the compliance matrix for an isotropic material. This compliance matrix is 6 by 6, which means it has 36 components. But now let me ask you a series of questions, or rather let's make a series of observations. In general, the compliance matrix seems to have 36 components, which could conceivably be all different from each other, but are they all different from each other? Or asked alternatively, in order to know every component of the compliance matrix for an isotropic material, that is what I am concentrating on presently. Okay, again, remember the argument is this always holds whether the material is isotropic or anisotropic, and there will be different types of anisotropy. For all types of anisotropy, this holds. So if it also holds for isotropy, then I can write also a compliance matrix, and so I put these equations or recast them in matrix form, and that's what I get. And now I ask the question, well, how many physical constants do I need to know, material parameters, in order to fully find the form of the compliance? Okay, take a few seconds. The answer is 2, right? So I see here 3 constants, Poisson ratio E and the shear modulus. But do I need to supply you 3 values? If you know G, you know all these values. You know that these are 0 if the material is isotropic, and these are 0, you know. And then if you know the Young's modulus, you know those. Poisson ratio, you know everything else, right? Do I need 3 values? No, because if you have an isotropic material behavior, you remember that G is equal to E over 2, 1 plus nu is a relation that you have to satisfy. There are only 2 constants, as we recall. And therefore, the 36 constants that seemingly appear at first are actually not, do not reflect the full reality. The reality is that you just need to supply me 2 values, namely, for instance, E and nu, or for that matter, any 2 of your choice, and I can find the full form of the compliance matrix. So the first message is that the compliance is a 6 by 6 matrix, but it may not end up having all 36 components independent from each other. They may depend on each other. That's the way they depend on each other, ultimately on just 2 constants, E and nu, for instance, for a case of isotropy. Okay? This will be the case for different types of anisotropic material behavior as well. Okay, so then, again, this form holds always we're just writing the corresponding generalized Hooke's law, or recasting it in that form as well. So we see that it also holds for the case of isotropy. And now, therefore, let me start a discussion that's going to be useful. Now, what I'm going to do is, or what I observe is, that we have a matrix 6 by 6 and it has sub-matrices, blocks, which are each 3 by 3. So this matrix here is a 3 by 3 matrix, this one as well, and that one as well. Okay? Now, these components of the strain have to do with normal deformations, and these with shear. And these stress components have to do with normal stresses, and these with shear. So to get any component in here, I take a row, multiply with that vector, right? So in order to calculate a normal component, I take this matrix, this portion multiplies the normals, this portion multiplies the shears, in this case it's 0, but in general multiplies the shears, and you get a contribution to a normal strain. So this submatrix, this block, connects or couples a normal mode of deformation to a normal stress. So this is normal coupling. This, for the same reason, couples or contributes to the normal deformation something that has to do with shear. In this case it's 0, but in general this multiplies shear, so if it were not 0, it would predict some contribution to normal strain due to shear stresses. We don't have that in isotropy, but let's wait for a few seconds and for a few minutes, or at least, and we'll see what happens in the case of isotropy. So I'm going to call that normal shear. Couples that one to that one. So by the same argument, this one takes a contribution in general. This multiplies that, contributes here, that multiplies that, contributes here. So this is shear to normal coupling. And this one couples shear to shear. All right. Now, that is a useful discussion, and the reason it is useful is because what we see here is a very specific material behavior that highlights the nature of isotropy. What we see here is that we have a isotropic material behavior in which if you apply normal stresses, you get normal strains, but because this matrix is 0, you don't get any shear strains out of it. Okay? If you have only normal stresses and no shear stresses, this and that will multiply this and this to get the shear contribution to deformation. But if you have no shear stresses, the multiplication or contribution is 0 of this block, sub-block with that component of those components of the matrix, and this multiplies a 0 block matrix, therefore you get no shear. So pure normal stress does not induce shear, or for that matter, if you have pure shear and no normal stress, because these components are 0, you get a 0 normal strain. Okay, so let's put those observations, those things I've said in an example. So let us imagine that we have a cylinder and I pull on it. Okay, so when I pull on it, I apply ultimately normal stresses. And my question is, well, what happens to this cylinder? And the answer, your answer, based on 231 intuition, let's say, is, well, it's trivial. Why are you asking? Because the only thing that will happen is that this thing will elongate, and that's it. Nothing fancy. But now I'm asking you, well, why, when I pull on this thing possibly does not twist. Okay, I'm not applying a torque. What I imply here is twisting, which is somehow some shear strain, right? So what I'm saying is I apply a normal stress and you predict some normal strain, and I completely agree with that. The question is, do I expect to see a shear strain? And your answer is no. Why would I have a shear strain? Well, you are saying so because you're assuming implicitly isotropy. What this relation says, tells us is that indeed, if you have only normal stress and this is 0, and you apply the normal stresses to get a shear strain, these would multiply these would have to be non-zero. And as a result of that, you would get some shear strains. But these are 0, and therefore you don't expect to see that. Which means that if these were not 0, I pull on something and it would twist. Sounds unnatural, but that's exactly what would happen. Now, another scenario. Let us imagine that we have, again, a cylinder. Same thing. And now instead what I do is I torque this thing. And so I apply some shear stresses. And my question is, well, what would happen as a result of that? Well, your expectation is that you would get some shear strain as a result of the application of those shear stresses. And my question is, well, is it conceivable that this thing also perhaps elongates a little bit? And your answer in normal circumstances would be no, nonsense. I wouldn't expect something like that to happen. And that expectation also is based on the case of isotropy. And so what you're saying is I only have shear stresses, and as a result of that, to get normal strains, this thing better be non-zero because I have no normal stress, and so these are ineffective presently, but these are 0, there is no normal shear coupling, and therefore I don't expect this. So it turns out therefore that if these terms are non-zero, then if you just apply a torque, this thing could conceivably expand, or it could contract depending on their values. Likewise here, if I pull, if there is shear normal coupling, then it could twist depending on the values either in that or the other direction. Okay? So these are the things that we are ultimately going to observe. So this has to do with shear normal coupling, and this has to do with normal shear coupling. Okay. Now, it finally turns out that if you have one, for sure you have the other one. So in other words, if you have a material that displays this type of interesting behavior, which certainly is not isotropic, it is anisotropic, then if you subject the material to this experiment, it will also display that. So if you have one, you have the other. And I'm going to tell you why in a second. All right. So what we've done is we've cast the generalized Hooke's law, which was for isotropy in that setting. And now what we are going to do, what we've done is therefore obtain the compliance matrix for the case of isotropy. And that's a very special form, namely for isotropy again. And we've observed a number of things, in particular, a large number of zeros, in particular, not all 36 components need to be provided. In the case of isotropy, only two need to be provided. And moreover, we've also observed in the nature of this, we've learned that the nature of that compliance matrix ultimately influences the way or the type of coupling that we have between shear and normal strains and stresses. All right. So now we want to go to the next step. In other words, well, what if I do not have isotropic material behavior? In that case, what does this compliance matrix look like? Okay, and that's the next thing we'd like to address.